Welcome to all in the lecture series of functional analysis. Now today in this lecture we see uniform boundedness theorem. The statement is, let sequence Tn be a sequence of bounded linear operator Tn which is from x to y, where capital X is a Banach space and capital Y is a norm space, such that sequence of norm of Tnx is bounded for every x belongs to capital X. Say norm of Tnx, it is less than or equals to Cx, where Cx is a real number and it is true for all n equals to 1 to up to so on. That means all the terms norm of Tnx, it is bounded by the real number Cx. Then in this case the sequence of the norm of Tn is bounded. That is, there is a C such that norm of Tn, it is less than or equals to C for all n equals to 1 to up to so n. That means here we have to given a sequence of bounded linear operator such that for every x belongs to capital X, each sequence norm of Tnx is a bounded sequence. That means norm of Tnx, it is less than or equals to Cx for every n. Then in this case the sequence of the norm of Tn, that means the sequence of norm of Tn, it is also bounded. That is we have to show. Now to prove this uniform boundedness theorem, we use the Bayes category theorem, and in that theorem as we show that if capital X is a complete metric space and it is written as the countable union of closed sets, then at least one AK contains a non-empty open subset. We use that result. Here we show that we construct AK. First of all, we construct the subset AK, which is a subset of X, and after that we are showing that this AK is a closed set. And then we show that, we prove that capital X, it is written as the countable union of AK. And then by Bayes category theorem, we get a non-empty open subset. So with the help of that non-empty open subset which is contained in some AK, and then with the help of this non-empty open subset, we prove the condition that norm of Tn, it is less than or equals to C for every n. So first of all we construct AK. So we start the proof. For every k belongs to the set of natural number. For every k belongs to the set of natural number, let AK subset of X be the set of all X such that norm of Tnx, it is less than or equals to k for all n. That is, we are writing AK be the set of all X belongs to capital X such that norm of Tnx, it is less than or equals to k for all n. This is the AK, which is a subset of capital X, because every element of AK is the element of capital X. Now after that, now this AK, this subset AK of capital X is closed. We prove it since we know that AK, it is always a subset of AK closure. Therefore here we have only to show that AK closure is a subset of AK. So we start with any arbitrary element of AK closure. Since for any X belongs to AK closure, by definition of the closure, there exists a sequence, say Xj in AK such that Xj converging to X. Now Xj converging to X, it implies that Tn Xj converging to X as j goes to infinity. Tnxj converging to Tnx. The reason is Tn is bounded. Here we have to given that Tn is a sequence of bounded linear operator. That means each Tn is bounded and every bounded linear operator is always continuous. And therefore here as a Tn xj, as xj converging to x as j goes to infinity, implies that Tn xj that converges to Tnx as j goes to infinity. But Tn xj converging to Tnx and norm is a continuous function, and norm is a continuous function. As norm is a continuous function, therefore Tn xj converging to Tnx for each n, it is also true for each n, implies that norm of Tn xj that converges to norm of Tnx for each n, and j goes to infinity. Now norm of Tn xj that converges to Tnx, and here we have to given that sequence xj, it is a sequence in ak, and the ak with the set of all those x for which norm of Tnx it is less than or equals to k, and therefore here we are getting that as sequence xj is a sequence in ak. Therefore by definition of ak, for each j, for each fixed j, norm of Tn xj it is less than or equals to k for all n, and therefore as norm of Tn xj that is lesser than or equals to k for all n, and for each fixed j, norm of Tn xj it is lesser than or equals to k. Therefore if I am giving it the equation number 1 and this is the equation number 2, then from equation 1 and 2 we get, therefore from 1 and 2 we get norm of Tnx, this is also less than or equals to k for all n, and as norm of Tnx it is less than or equals to k for all n, implies that x belongs to ak. That means for any x belongs to ak closure, we are getting that x belongs to ak, and this implies that ak closure is a subset of ak, and this implies that ak is closed for each k belongs to the set of natural number. Now we show that capital X equals to union k is running from 1 to infinity ak, that is we show. So as we know that for each k ak it is a subset of x, and as for each k ak is a subset of x, therefore union k is running from 1 to infinity ak, that is also the subset of x. This is the one part. I am giving it the equation number 3 also for each x, the given condition is that for each x norm of Tnx is bounded. That means for each x belongs to capital X, there exists some k belongs to the set of natural number such that norm of Tnx it is lesser than or equals to k for all n. This is the given condition, because here we have to given that the sequence of norm of Tnx it is a bounded sequence, and therefore here for each x belongs to capital X, there exists k belongs to the set of natural numbers such that norm of Tn x, that is less than or equals to k, and this implies that x belongs to the ak, and therefore that means for every x belongs to capital X, there exists k belongs to n such that x belongs to ak. This implies that x, it is a subset of union k is running from 1 to infinity ak, because every element of capital X is contained in some ak, and therefore x, it is a subset of union of ak. Now we are giving it the equation number 4, and therefore combining equation 3 and 4, therefore from equation 3 and 4 we get x equals to the union k is running from 1 to infinity ak. That means x is written as the countable union of ak, where for each k ak is closed. Where for each k ak is closed. And therefore also here we have to give one condition that capital X is a Banach space. As capital X is complete, thus by Bayes category theorem, by Bayes category theorem, at least one AK contains a non-empty open set. By Bayes category theorem, at least one AK contains a non-empty open set, and therefore here thus for some AK0, say here we are considering that AK is nothing but AK0, thus for some AK0, the ball, open ball B0, that is equals to the ball B with center x0 and radius r. B0, it is contained in AK0. That means there exists, as Bayes category theorem says, that for at least one AK contains a non-empty open set, and therefore here we are taking that non-empty, AK, it is equals to AK0 contains the non-empty open set. We know that every ball is a open set, and therefore this is the ball with center x0, that means it is always non-empty, and therefore we are considering that non-empty open set as the open ball B0, it is equals to B of x0 comma r with radius r and center x0, and it is contained in AK0. Now with the help of this center point x0 and we define another point of capital X. We considering, let small x belongs to capital X be arbitrary, and it is also non-zero, be arbitrary non-zero, and we set another point z, that is equals to x0, which is the center of this ball, plus gamma into x, where gamma, it is equals to r divided by 2 into norm of x. In this way we define another point z with the help of this arbitrary point x and the center of the ball x0. We define z. Then norm of z minus x0, it is equals to norm of gamma x, it is equals to, as gamma is a real number, therefore it is equals to gamma into norm of x, that is equals to, putting the value of gamma, that is equals to r divided by 2 into norm of x into norm of x. These two get cancelled and it is equals to r by 2. That means here we are getting that is norm of z minus x0, it is equals to r by 2 and it is strictly lesser than r. This implies that norm of z minus x0, it is strictly lesser than r. And as norm of z minus x0, it is strictly less than r, implies that the distance of the point z from the center x0, it is lesser than r, and this implies that z belongs to the ball with center x0 and radius r, and that ball is nothing but b0. That means here we are getting that z belongs to b0. Now as x0, it is the center of the ball b of x0 comma r, and therefore that point it is always contained in that ball, and this ball it is contained in ak0. As this ball is contained in ak0, therefore by the definition of the ak0, here we have norm of Tn x0, it is less than or equals to k0 for all n equals to 1, 2 up to so on. And therefore as here here norm of Tn x0, it is less than or equals to k0, it is less than or equals to k0, and also as here we are getting that z, it is contained in the ball b0 and b0 is also contained in ak0. We also have z belongs to the ball b0 as we proved that, and b0 it is contained in ak0. This implies that norm of Tn z, that is also less than or equals to k0. It is again for all n equals to 1, 2 up to so on. Now with the using this, now we are taking the norm of Tnx. For this, first of all, as we define z, it is equals to x0 plus gamma x. Therefore x, it is equals to 1 by gamma, and in bracket we have z minus x0. This is the value of x by using the definition of the z. Then for all n, norm of Tnx. Now here we are putting the value of x, norm of Tn into norm of Tn of 1 by gamma into z minus x naught. Now 1 by gamma, it is something a scalar, and therefore it is lesser than or equals to first of all we are writing it is equals to 1 by gamma into norm of Tn of z minus x. It is equals to 1 by gamma into norm of Tn of z minus x naught. Now it is equals to 1 by gamma into norm of Tnz minus Tn x naught. It is lesser than or equals to 1 by gamma into norm of Tnz plus norm of Tn x naught. And as we prove that norm of Tnz, it is less than or equals to k0 for all n. Similarly, norm of Tn x0, it is less than or equals to k0 for all n. With the help of these two inequality, we are writing that it is lesser than or equals to 1 by gamma. Now it is lesser than k0 plus k0. That is equals to twice k0 by gamma. Now putting the value of gamma, it is equals to twice k0. The value of gamma, it is, as here we know the value of gamma, it is equals to r divided by 2 into norm of x. Putting this value here, we are getting that twice k divided by r into 2 norm of x. This is equals to 4k by r into norm of x, and therefore here we are getting that norm of tnx, that is norm of tnx, it is less than or equals to 4 it is k0, 4 k0 by r into norm of x. Now it is true for all n, and therefore as it is true for all n, therefore we are getting that therefore norm of tn, that is equals to supremum of all norm of x equals to 1 norm of tnx. Now it is equals to, just putting the value of here, now for each n norm of tnx it is less than or equals to this, and therefore this supremum it is also less than or equals to 4k0 by r as norm of x equals to 1. Therefore it is less than or equals to 4k0 by r. We are putting it is equals to c. Then norm of tn, that is less than or equals to 4k0 by r, that is we are putting that it is equals to c. Then we get that norm of tn, it is less than or equals to c, with c equals to 4k0 by r, and therefore as it is true for each n, we get that the sequence of norm of tn is bounded, and hence the result.